We're very happy to have Soumyadeep Chaudhuri from Brussels University, and today he will talk to us about semi-classical analysis of finite cutoff JT gravity on a disk. Please.
Okay. Thanks for inviting me to give this talk. Uh, so I'm going to talk about a work that I did in collaboration with Professor Frank Ferrari, who is a faculty member in ULB. And this work uh, deals with JT gravity, which is a two-dimensional theory of quantum gravity. So to understand quantum gravity, it is very useful to consider models where one has some kind of analytic handle so that one can do computations. And such two-dimensional models are particularly useful for this purpose. And a lot of progress has been made over the last few decades in studying such two-dimensional models. The model that has been studied most extensively is Liouville gravity. And by now, many exact results are known for this model, that is Liouville gravity, like the well-known results of DOZZ and FZZT, which compute the partition function and correlation functions exactly in Liouville gravity. But in the last few years, there has been a lot of interest in a different class of 2D theories, which are called this Jacques-Teitelbaum gravity. And the distinctive feature of these theories is that the allowed metrics in these theories correspond to constant curvature, constant bulk curvature. And the motivation for studying such theories came from the observation that in the negative curvature case, this theory is holographically dual to SYK-like models in the Schwarzschild limit, in a particular limit, basically the low energy limit of such SYK-like models are holographically dual to the negative curvature JT gravity theory. And moreover, another reason for being interested in these theories, was that it also provides an effective description of the near horizon region of nearly extremal black holes in higher dimensions. Okay, so these are the reasons why people were interested in studying JT gravity thoroughly. So a lot of work has been done in studying these theories, but despite these works, several questions have not been addressed adequately. So here I present a list of such questions. So the first question is how to analyze JT gravity beyond this Schwarzschild limit, and also how one may be able to understand the zero and the positive curvature case. Most of the studies that have been done are for the negative curvature version of JT gravity because of the reasons that I mentioned. The motivations came from studying the negative curvature model, but one can also study these the zero and the positive curvature case, which are also interesting, and the positive curvature case in particular may be relevant for understanding de Sitter geometries. So de Sitter gravity in de Sitter like space. And also it would be good to understand in detail what happens when one couples matter to these theories. So in the past, there have been some works which attempted at studying this first question, that is going beyond the Schwarzschild limit in the negative curvature version of the theory, and which corresponds to putting a finite cutoff in the dual quantum mechanical model that I was talking about, SYK-like models. It corresponds to putting a finite cutoff on this effective description. And these are three examples: this Kitaev-Su model and Stanford Young paper and Luca Ilescu and some other authors' paper that appeared in the last about 4 years ago. And the Kitaev-Su model was the first proposal for such finite cutoff version of GT gravity. But there are some problems with these proposals, which I'm going to talk about now. So Kitaev-Su proposed a finite cutoff description, which is based on assuming the boundary of space-time being the trajectory of a Brownian particle. So they assume that the boundary is just the trajectory of a Brownian particle, completely random motion. And this is a well-defined statistical mechanics model, but it turns out that it does not correctly describe a theory of quantum gravity. Because it does not follow from, I mean, diffeomorphism invariance and so on. I mean, like diffeomorphism invariant theory of metrics. It does not correspond to that. On the other hand, these other two papers that I mentioned, Stanford Young and ESU and others. So these papers both they rely on the boundary consisting of self-avoiding curves. And moreover, the paper by Iliescu and others, they also consider only smooth boundaries. So again, as our understanding is that this only captures a part of the allowed configuration. This is a subset of the allowed configurations. These are not typical configurations that appear if you consider the full path integral, gravitational path integral. This is our understanding about their works, but yeah. So recently, there have been some works which attempt at understanding the gravitational path integral in GT gravity from first principles, that is both from a lattice point of view, from a lattice version of the theory, as well as in the continuum limit. So these are the references. These works were done by my collaborator, Frank Ferrari. These appeared earlier this year. And these works argue that the correct boundary configurations for the gravitational path integral are self-overlapping curves, which correspond to immersions from the base manifold to the target manifold of constant curvature. So the point is that if you consider, let's say, the base manifold is a disk, and you consider immersions from this disk to the target manifold of constant curvature, which is, say, in the case of negative curvature, just hyperbolic space. In the case of zero curvature, it's just flat space. In the case of positive curvature, it's the sphere. So this mapping defines a metric on the disk by a pullback. Okay. This immersion that takes you from the disk to the target manifold, its pullback defines a metric on the disk itself. The typical curves that contribute to such a path integral are not smooth, but are rather fractals. That this was also found in this. This was also argued in these papers that I mentioned. And furthermore, there are curves that can bound multiple bulk configurations with constant curvature. That is, if you just specify the boundary, it does not completely fix the metric that is defined in the bulk. There can be multiple bulk configurations that have the same boundary. So these are some genuinely new points that were discovered in these papers. And these observations have motivated us to explore this gravitational path integral in finite cutoff GT gravity in a control setup where a semi-classical analysis can be performed. So computing the contributions of all these configurations is a challenging task. So the idea is to work in a regime where one can actually calculate the gravitational path integral to some approximation and up to some approximation. Uh, and one convenient way of doing that is to work in a regime where you can you can use a semi-classical analysis. And this is the idea that we explored. Okay, and this is what I'm going to talk about today. Is there any question? Let me just go on. So to attain this control setup, we have borrowed an old idea that was employed by Zamolodchikov to gain some understanding of some preliminary understanding of the gravitational path integral in the Liouville theory. And the idea is to couple gravity to conformal matter with large negative central charge. So this then it's not a unitary theory, but nevertheless you want to, what it does is that it allows you to do this kind of semi-classical analysis. So because in this case the gravitational path integral is dominated by a saddle point, and by systematically taking account of the fluctuations about the saddle point, one can actually do some computations and gain some intuition about the quantum gravity path integral. And I will, in this talk, I will present this idea in the context of JT gravity on a disk in all three cases, that is negative, zero, and positive curvature. And I will explain that in this regime, the partition functions of these models can be systematically expanded in a perturbation series. And the small parameter in this perturbation series is 1 over mod C, C being the central charge of the CFT that is coupled to gravity. Okay. So let me explain the setup. So consider JT gravity on a disk on a disk which I'm denoting by D, and let's minimally couple conformal matter to the metric. Okay. So the action takes this form. So you have the JT gravity action plus the action of the conformal field theory in a background G. G is the metric. Okay. And the JT gravity action is of this form, where you have so eta is plus 1, minus 1, or 0, corresponding to whether we are considering JT gravity negative curvature or zero curvature. So phi in this action is a dilaton field that imposes the constraint of constant curvature in the bulk. Okay. So it's like a Lagrange multiplier essentially. So it imposes the constraint of constant bulk curvature, but the K is the extrinsic curvature in at the boundary. So this we do not want to impose any constraint on this extrinsic curvature at the boundary. So and for that we do not allow the field phi at the boundary to fluctuate. Okay. So we take it to have we impose a particular boundary condition where phi is takes a uniform value, that is a constant value at the boundary, and we keep it fixed. We do not let it fluctuate. Okay. And lambda naught that I have entered here is a bulk cosmological constant term. And this is introduced explicitly for the zero curvature case. For and what I'll show in a moment is that for the positive or the negative curvature case, you in any case this uh, extrinsic curvature term that I've written down, that effectively contributes to a bulk cosmological constant. So one need not introduce a lambda naught explicitly. So that's why yeah. So this term, this last term, but I've taken it to vanish for the non-zero curvature case, because in any case there would be an effective bulk cosmological constant generated from this extrinsic curvature term itself, as I will explain in a minute.
It's just eta by L squared. Is that true?
Sorry,
Lambda naught is just eta by L squared. I mean, I'm just asking.
lambda naught. No, lambda naught's value can be anything. I mean, it can take any value.
What
Lambda naught. There's no connection between the bulk cosmological constant and the curvature of the space.
I see.
It's an explicit area term that I'm introducing.
I see.
But I'll come to the discussion of the cosmological constant in a moment. I'll discuss it in more detail. So okay, so we can set this constant Gn, the overall constant, the Newton's constant, to be equal to 1 by rescaling the field phi and in the flat case lambda naught. And for the non-zero curvature case, we work in units where L is equal to 1. Okay. So from now on, I'm going to set Gn and L equal to 1.
Can I ask a question?
Yes.
What is the boundary condition on the metric?
There's you perform an integral. So at this level, you perform an integral over. There's no boundary condition on the metric at all. Okay. So you allow the metric to fluctuate. What the phi field is going to do eventually is to impose the condition of bulk constant curvature. Eventually.
Additional problem, right?
Sorry?
This action should also have a well-defined variational problem.
Yes. So that there's no problem with that, because this is the given Hawking term is added. This phi k is a given Hawking term, which
Put Dirichlet condition.
sorry, what?
That takes care of the variation, like that makes the variation 0 when you are putting Dirichlet condition on the. But here you are
No,
allowed.
why? Dirichlet boundary condition, why? On the metric?
Yeah,
Why? No. Why should I put Dirichlet boundary condition on the metric?
I thought the extrinsic curvature term makes the boundary metric.
No, there's no reason to impose. In fact, the point is that, as I will argue in a moment, if you impose additional boundary conditions on the metric, the point is that it will get there won't be any fluctuation at all. I'll explain it in a moment, but you have to allow the the boundary extrinsic curvature to vary. There's no additional constraint at that level. Sorry?
Please go ahead. Maybe I'll think about.
So integrating over this dilaton field phi in the bulk imposes the constraint of r equal to 2 eta that I was mentioning. And using the Gauss-Bonnet theorem for the disk, this leads to the boundary term in in the JT gravity action to take this form. So you have this integral over ds phi k. So phi is taken to be a constant at the boundary. So you have phi b, and this integral over dsk. This by Gauss-Bonnet theorem is related to there's a term like 4 pi phi b, and then there is this area term minus 2 eta phi b integral over d2x square root of g, which is just the area. And so what one can see is that this phi b, this boundary value of the dilaton field, this contributes to the effective bulk cosmological constant in this way. So you have an effective bulk cosmological constant where lambda is equal to 2 eta phi b plus 1 minus eta square times lambda naught. Okay. So as I was mentioning earlier, so you have although there's no contribution from this lambda naught term in the eta equal to plus minus 1 term, eta equal to plus minus 1 case, nevertheless, you have a bulk cosmological constant emerging from the fact that you're emerging from this thing, the Gauss-Bonnet theorem, from the extrinsic curvature term. Okay. So, and the point to note here is that we do not impose any condition on the sign of this cosmological constant, or rather this phi b. At the moment, we do not impose any condition on the value of this boundary field, let's say, boundary value of the dilaton field. And so there's no obvious connection between the sign of lambda and the value of eta. Okay. So, okay, so and what we want to compute is the partition function of this model for finite boundary lengths. Okay. So, however, in this work that I mentioned earlier, this that appeared in February by Professor Frank Ferrari, it was argued that this boundary is typically a fractal curve with no standard geometric length. So this boundary length integral over e to the power d, sigma, let's say, ds or integral over ds, this doesn't make sense because the boundary is a fractal. So instead of this naive length, you have a renormalized quantum length parameter beta with a Hausdorff dimension dh is equal to 1 by nu, such that beta to the power nu has the dimension of length. Okay, so like for instance, if you think about the lattice model, let's say, so you have so if you want to take the continuum limit, you take the lattice spacing to 0, and you whereas this the number of while scaling the number of while scaling the length as well, but to define an appropriate continuum limit, one may not have something like the lattice spacing times the number of such or the length in the lattice model approaching a particular value, but it can be that the scaling works in a different way. That is, the lattice spacing goes to 0, the length in the microscopic model that goes to infinity, but there's a relative power of this length, this microscopic length, that you have, which multiplies with the lattice spacing, and that approaches a constant value. So that's what fixes this nu. Okay. So for c less than 0, this exponent nu is given by, it was found, an exact expression was found for this for this exponent that I mentioned, the Hausdorff dimension. And the thing to note is that in the limit c tending to minus infinity, this nu approaches the value 1. And thus, in this limit, in the c tending to minus infinity limit, one can identify beta with the length L. And by taking into account finite c corrections on top of this, on c tending to minus infinity limit, one can find an anomalous dimension for L, which should be consistent with this, with what I have written, nu, the expression for nu that I have written. And I will show that the first subleading correction in the 1 over mod C expansion that we do to the partition function shows a hint of this anomalous dimension, which is consistent with the expression, the exact expression of mu that is written here. Okay. Is there any question on this?
Can I just ask a question? I think this is related to the earlier question. That when you
Yeah.
integrate over the metric fluctuations,
Yeah.
are you limiting yourselves to normalizable modes of the metric on the background radius to geometry?
I'm no, I'm integrating over all possible metric fluctuations that all possible metric fluctuations sigma, or all possible metric fluctuations in the boundary.
The diverge at the boundary.
I'm considering a finite configuration, right? Finite length configuration. I'm not considering it to go to.
Right, so you are including those as well in the integral.
Yes, so I'm not considering things that go to asymptotic infinity. I'm considering a finite boundary, right?
Okay. Yeah.
And there I'm integrating over all possible fluctuations.
I see.
I'm not considering the case that where this boundary is close to is asymptotically going to infinity.
Okay.
So I'm integrating over all possible fluctuations and at the boundary.
Okay.
Okay, so the partition function of our interest is this. So we have this integral over the metric, the dilaton field with this constraint, and you have this e to the power minus sjt, and then this ZCFT comes from the integral over the matter fields, the conformal theory that I have introduced, that I've coupled to gravity. Okay. So the gauge symmetry in the theory is the group of diffeomorphisms of the disk. And one can partially fix the gauge by taking the metric to be of the form G is equal to e to the power 2 sigma times delta, where delta is the standard Euclidean metric on a disk of unit radius. Okay. And then the integral reduces to a path integral over phi, the dilaton field, sigma, the conformal factor sigma, and the boundary value of sigma, which we denote as small sigma. Okay, so we choose to work in this conformal gauge, and the constraint on the small sigma is that its integral over d theta e to the power sigma should be equal to L. Okay. So in this conformal gauge, the dependence of this partition function for the CFT on the background metric is of this form. So it's just there's a very simple dependence, universal dependence, in fact, which only depends on the central charge of the CFT that is coupled to the background metric. So and the dependence is of this form. So you have ZCFT e to the power 2 sigma times delta is ZCFT of delta for the just the flat background times this exponential c by 24 pi, and there's a multiplied to an action, and this action is called the Liouville action, which is written down here. So this is just the first term is just it's like del it's grad sigma whole square, basically, written in radial coordinates. That's all. And in addition to this contribution, which comes this Liouville kind of term that appears due to the integral over the matter fields. In addition to this, the gauge fields that emerge from the gauge fixing are governed by a CFT with central charge -26. And hence its dependence on the metric or the conformal factor sigma is exactly of the same kind. So where C is just replaced by -26. Okay. So finally you have then the partition function is ZCFT. You have an overall factor which doesn't depend on the background metric at all. ZCFT delta times Z ghost delta. And then there's an integral over this conformal factor in the bulk, conformal factor in the boundary, the dilaton field in the bulk, and with this constraint that integral over e to the power sigma, this should be equal to L. There's a delta function that imposes this. And you have this exponential C minus 26 by 24 pi, the Liouville action, and minus SJT, the JT gravity action. Okay.
So this L is the length, the cutoff length of this boundary.
Yeah. That's. And this is finite. This is taken to be finite. That's why I'm saying that it's not at asymptotic infinity. I'm not working at asymptotic infinity. I'm keeping L finite. Okay. So this is the path integral that I want to evaluate. Okay. So after choosing to work in this conformal gauge, there's a residual gauge symmetry. So the choosing the conformal gauge fixes the diffeomorphism invariance that we had earlier, only partially. And there's a residual PSL2R gauge invariance, which consists of automorphisms of the disk. Okay. And these measures that up till now, I've not mentioned anything about the measures, d sigma, d small sigma, or d phi, these measures. So the measures, d sigma and d small sigma, should respect this gauge invariance. We want to choose these measures so that they respect the gauge invariance, this PSL to the residual PSL to our gauge invariance. So to ensure this, we consider ultra-local measures which satisfy this gauge invariance. And these measures are derived from the metrics in the field space that are given here. Okay. So this PSL2R, we want to further fix this PSL2R gauge invariance as well. At least, so the PSL2R gauge invariance has 3 real parameters. The PSL2R group has 3 real parameters. We want to reduce it such that it's a non-compact group. So we want to reduce it so that it reduces to a compact group, just a compact group. So we fix 2 of the parameters by imposing these conditions that the integral over e to the power sigma over the full angle 2 pi is equally distributed for 3 segments from 0 to 2 pi by 3, from 2 pi by 3 to 4 pi by 3, and from 4 pi by 3 to 2 pi. These integrals are the same. That is, each of them are L by 3. So the overall integral is L. So here we have essentially just two constraints. We impose 2 conditions, and the other one is guaranteed by the fact that the full integral is L. Okay. So we fix this PSL2R gauge symmetry, this residual gauge symmetry, by imposing these conditions. And this further introduces a Faddeev-Popov determinant, which is proportional to this e to the power, this gauge fixing, this residual gauge fixing. This introduces a Faddeev-Popov determinant, which is proportional to e to the power sigma 2 pi by 3, sigma at 2 pi by 3, plus sigma at 4 pi by 3. Okay. So then the partition function takes this form. So you have an integral over these conformal factors sigma at the bulk, in the bulk, its boundary value, the integral over the boundary value, integral over d phi, and you have these delta functions imposing the conditions that I mentioned earlier. And you have C minus 26 by 24 pi, the Liouville action times the Liouville action. minus SJT, and you have these sigma at 2 pi by 3 and plus sigma at 4 pi by 3 coming from the Faddeev-Popov determinant corresponding to this gauge fixing, this residual gauge fixing. Okay. And notice that this form of what appears within the action suggests that in the C tending to minus infinity limit, it may be dominated by a saddle point configuration. Okay, because you have this Liouville action which multiplies with a term like C, and if you take C to minus infinity, it may be dominated by a saddle point configuration. This is just a suggestive note here. I'll flesh it out in more detail in a moment. So integrating out this dilaton imposes the constraint of constant bulk curvature. Okay, and in the conformal gauge, this reduces to this Liouville equation: delta sigma is equal to eta. Okay, so in the conformal gauge, this curvature is just 2 times delta sigma, and that gets equated to 2 eta. And here delta is the positive definite Laplacian operator in the background. G is equal to e to the power 2 sigma delta. Okay, and it is related to the Laplacian operator in just flat space in this way. So delta is e to the power minus 2 sigma delta naught, where delta naught is the Laplacian operator, positive definite Laplacian operator, that is minus of what we usually call the Laplacian, minus of grad square. That's the delta naught is minus of grad square, and delta is e to the power minus 2 sigma times delta. So you have this Liouville equation, which is imposed by after integrating out the dilaton. Okay, and this gives you so after integrating out the dilaton, you have this contribution delta to delta sigma minus 2 eta, and you have an effective action. You have these delta functions coming from the PSL2R gauge fixing and the overall length constraint, and you have an effective action which is of this form. Okay, you just have the area term coming from the JT gravity part, and you have this these other terms minus sigma 2 pi by 3 minus sigma 4 pi by 3 coming from the PSL2R gauge fixing. A is the area of the disk. Okay, lambda is the cosmological constant, and SL is the Liouville action. So you have this is what you are left with. So now let me explain the regime that I'm working in. So we work in a regime where C is a large negative number, as I was mentioning. We take C to minus infinity, and to not completely ignore the area term, we take it to scale with C as well, scale linearly with mod C, so that its contribution is not ignored. When we take this limit, its contribution, the area term's contribution is not completely ignored. We take it to scale with mod C. And then we find that in this regime, the path integral is dominated by a saddle point. Okay, when we take this limit, we find that the path integral is dominated by a saddle point. Mu is the proportionality constant between lambda and mod C. Okay, so we take mu, and we do not impose any condition. As yet, we do not impose any condition on this parameter mu. So mu is now the effective bulk cosmological constant that appears. So now, we have this S effective, the effective action. We can split it into 2 pieces. One which has an explicit factor of mod C multiplied to it, so which is SL plus mu A. And then there is this plus 13 by 12 pi SL as well, because we had, if you remember, we had this minus C by plus 26 by 24 pi SL. This was the contribution of the Liouville term. So I'm just splitting it into two pieces. So there's one piece which is mod C by 24 pi, and then there is another piece which is plus 13 by 12 pi SL. Okay. And this what I'm calling the classical action is SL plus mu A. That's it. And extremizing this action, this classical action with the constraint, with these constraints that appeared, the constraints that are given here, the constraint of constant bulk curvature, and the constraints that emerge from PSL to R gauge fixing, and the constraint of overall length being having a fixed value. So with these constraints, we have to find the saddle point configurations, sigma star, which I'm calling sigma star, and its boundary value, which is small sigma star. Okay, this is the idea.
So
and then
Soumyadeep, would it make a lot of difference if rather than scaling lambda with mod C, you scaled it with mod C minus 26? Because anyway, mod C is a large number, no?
Yeah. Okay. Yeah.
If you scaled it with mod C minus 26, you won't get this 13 by 2 pi term, right? Wouldn't that?
No. This lambda gets multiplied with A. It does not get multiplied with SL. These two are different terms, no?
Yeah, they're two different terms, but if I had taken lambda to be proportional to mod C minus 26 or mod C plus 26.
And taken mod C plus 26 as
then you would not get any extra SL, right? In the next slide.
Yeah. Okay. So that's just like essentially redefining mu. Yeah. It's not so important. Yeah, but yeah.
But
you can.
So you would just get the sigma terms then. You would not. There's no reason why
it's a way of splitting the terms. Doesn't make much of a difference, but the idea is that it's what you call mu gets readjusted. That's all.
Yeah, but S effective will not will be completely. So then there'll be an S classical that full all SL will come with a mu A if you have defined it that way.
Yeah. Okay. Yeah. Okay. Okay. So the point is that this, and then after finding the saddle point, one can express the field configurations near the saddle point in this way. So you have the sigma star plus a fluctuation term, which is like capital Xi divided by square root of mod C. This is like the H bar expansion, actually. I mean, like just as you do H bar expansion in quantum mechanics when you try to study semi-classical, do a semi-classical analysis, you expand in such powers of 1 over H bar. And similarly, here you have to expand in square root of mod C. And there's a corresponding expansion of the boundary value of the field as well, which is of this form. So this is capital Xi by square root of mod C, and this is just Xi, small xi by square root of mod C. And we wish to retain terms up to first subleading order in 1 over mod C expansion of log z eta, the log of the partition function. So this is the idea. Okay. So now, integrating over the fluctuation of the bulk field is simplified by this delta function imposing delta sigma is equal to eta. And near the dominant saddle point, there is a unique solution to this equation. This delta sigma equal to eta. Near the dominant saddle point, there's a unique solution which fixes the bulk fluctuation field Xi in terms of the boundary fluctuation field small xi. And this is the essential point that I was mentioning, that if you try to impose some kind of a boundary condition on the metric, the bulk fluctuation, it won't be consistent with the fact that so corresponding to a boundary fluctuation field Xi, there's a unique bulk fluctuation field. If you try to freeze the boundary fluctuation, it freezes everything. There's nothing left actually. So that's that was the point that I wanted to make. That if you allow this boundary fluctuation field xi to, or what can happen is that the choice of the conformal gauge itself may get spoiled. So because after going to the conformal gauge, you are just left with this boundary fluctuation field xi, and if you try to impose conditions on xi, it completely fixes everything. There's no degree of freedom in the problem. Okay, so and we may denote this unique solution to the Liouville equation as xi, capital Xi with the subscript small xi. Okay, and so then the integral over the bulk fluctuation field is just, one has to convert this delta function, delta of 2 delta sigma minus 2 eta, to delta of this xi, the capital Xi minus capital Xi small xi, this solution corresponding to small xi. And when you try to convert this delta function to the delta function of the field, this fluctuating field, a Jacobian will arrive. Jacobian will appear, right? When you try to convert this delta function from delta function of this operator to a delta function of this of 2 delta sigma minus 2 eta to the delta function over the fluctuating fields. And up to the order that we are interested in, this Jacobian is of this form. Okay, where delta star is the positive definite Laplacian operator for the metric e to the power 2 sigma star times delta. Okay, and the subscript d indicates that the functional determinant, this functional determinant is to be evaluated with Dirichlet boundary conditions. Okay.
One question.
Yeah.
You are taking C goes to infinity limit before taking this cutoff L to anything, like you are really working in finite L. Is it?
I'm working in finite
or
L.
you want
There's
to do anything with the L?
I'm not doing anything with L.
Okay,
L
okay.
is finite.
Okay.
L is not large. There's no assumption on L. But I'm taking C to be.
Yeah.
I'm doing an expansion in 1 over mod C.
Yeah.
That's the idea.
So just a question. So this Z you want to calculate eventually in terms of functions of what?
L and mu.
L and mu. Mu is the cosmological constant. Okay.
Yes.
Okay. So the length of the boundary, the physical length of the boundary and the cosmological constant.
Yes.
And so because there are a lot of determinants and there are a lot of constants you're dropping, you're saying all those constants are independent of this L and mu. Is that the point?
Yes. The constants that I dropped were this CFT delta and ZGH delta, right? These
Okay.
do not depend on the boundary, on the metric at all. This L is determined by the metric, right?
Okay.
So these do not depend on this. This is defined on, these are CFTs, the partition functions of the CFT is defined on the unit disk with delta, So I've not dropped any other constant, have I? I mean, like, I don't remember.
So you're saying the CFT does not depend on the size of the disk, CFT partition function?
It would depend, but the delta is the unit disk with the disk with the unit radius.
Okay.
And the dependence is given by the background. The dependence on the background metric is of this form, right? That I wrote down. But the point is that this L is fixed by this metric, right? And so the dependence on the metric is completely, I've taken care of that. What I've ignored is ZCFT delta, which does not depend on the metric at all. It's for the unit disk with unit radius.
Okay.
Okay. Okay. So this is the point. Yeah. Right. So after you integrate over this, integrate over the bulk fluctuating field. So there are these terms in this expansion that I'm doing and retaining terms up to 1 over mod c. If you truncate at this order, then the partition function is given by this e to the power minus mod c by 24 pi SCL sigma star. There is this 13 by 12 pi of the times SL, and then sigma star at 2 pi by 3, sigma star 4 pi by 3, minus this ln of mod determinant delta star minus 2 eta that appears from the Jacobian that I mentioned. Jacobian coming from converting the delta function of 2 delta sigma minus 2 eta to the bulk fluctuating field, and then you are left with an integral over the path integral over the boundary fluctuating field, boundary field xi. Okay, and this boundary path integral is of this form, where you have an effective action which is quadratic plus higher order correction, order 1 over mod c corrections. And this is effective. I'll write down, I'll give an explicit form for this quadratic effective action in xi. But this is the idea. So you have to, so basically one has to, the crucial points is to determine, the saddle point, and then calculate this log determinant that comes from integrating the bulk modes, bulk degrees of freedom, and then one has to calculate this boundary path integral. So these are the non-trivial steps in the whole process, in the algorithm to calculate the partition function in this procedure. Okay, and then one can express this partition function as, sorry, there should have been a log. It's log z eta. I missed the log. Log z eta, that is mod c f0 eta plus f1 eta, and then there are higher order corrections, 1 over mod c and 1 over mod c square, these kind of corrections. And we have evaluated this leading order term, which comes from just determining the saddle point and evaluating SCL, and the subleading term, which requires the computation of the rest of the things. Okay. And okay, so we evaluate these quantities for the different values of eta. This eta is just a superscript to it's not a power, it's just a superscript to distinguish the different cases. Okay. So what are the saddle point configurations in this whole prescription? So for eta equal to 0, that is for flat JT gravity, the saddle point is a rotationally invariant disk of perimeter L. Okay, so we have sigma star is equal to ln L by 2 pi. That's it. So the saddle point has to be evaluated with the action, but with also by extremizing the action, but while preserving the constraints. Okay, the constraint of overall length and the constraint imposed by fixing the PSL2R gauge invariance. So you have to actually solve this classical problem with the action as well as these constraints, and what you get is that the saddle point is a rotationally invariant disk in just flat space with radius with perimeter L. And the sigma and the sigma star, that is the saddle point value of sigma, is ln L by 2 pi in the eta equal to 0 case. In the eta equal to -1 case, the saddle point is similarly a rotationally invariant disk of perimeter L, but in the hyperbolic plane. Okay, in two-dimensional hyperbolic space. And this sigma star is given by ln 2 r naught by 1 minus r naught square rho square, where r naught is determined in terms of L in this way. Okay. So in the positive curvature case, when L is less than 2 pi, there are two rotationally invariant saddle point configurations. And these are sigma star with 2r 0 greater than divided by 1 plus r 0 greater than square rho square, and similarly for less than. And what do these greater than and less than correspond to? They are dependent on L in this way. Okay. And these configurations are basically diffeomorphic to two disks on the round sphere, which are bounded by the same circle of perimeter L as shown in this figure. So if you draw a circle on a sphere, it would separate the sphere into two parts, right? Two segments. And these correspond to these configurations that I've written down. They correspond to precisely those parts, those two segments. Sigma star and sigma star greater than and sigma star less than. So one of them will have a larger area, and that's what that's what is given. That's what corresponds to greater than sign, and the other one will have a lesser area, and that's what corresponds to this less than sign. And we call the disk with the larger area as the large disk, and the one with the smaller area as the small disk. And the two disks merge when L is equal to 2 pi. That is when you consider something along the circle along the equator, let's say. So then the two disks are exactly identical. And for L greater than 2 pi, there's no rotationally invariant saddle point, at least. There may be saddle points that are not rotationally invariant, but as yet we have not actually explored this in detail. Whether there are, when you take L greater than 2 pi, if there are saddle points that are not rotationally invariant, that we have not explored in detail, but we restrict the discussion for the positive curvature case to L less than 2 pi henceforth.
For L greater than 2 pi, these saddle points themselves will be there, right? They'll just become complex or something.
Yes, that's
But there'll still be saddle points in some sense, right?
Yes, but we have not really done a thorough analysis for this case. That's what I'm saying.
Yeah,
So,
sorry, I got a yeah, please finish.
Yeah, so in this talk, I'm going to restrict my attention to this L less than 2 pi. It might be that for L greater than 2 pi, there are complex saddles. These saddles just become complex. It's possible, yes.
Okay, but could you just remind me, like this cosmological constant was you have set it to something? Maybe
No. The cosmological constant. The point is that these saddle points don't depend on the cosmological constant. The value of the S classical that depends on the cosmological constant. The saddle points themselves, so you have S classical that depends on cosmological constant, but the point is that one has to remember that the constraints that this classical solutions need to be found by extremizing the action with the constraints. And when you impose the constraints, you can show that these are indeed saddle points. But the value of the classical action is determined, indeed has the cosmological constant. And hence
there's a mu dependence.
There's a mu dependence in the classical action, but not in the saddle points themselves.
Okay, but that's like a way to parameterize. So you've chosen a coordinates as that, right? Yeah. Okay. Fine. So anyway, you're saying the final answer, the partition function would
depend on mu.
On the saddle point will depend on mu.
Yes.
Okay.
And for this, yeah.
Sorry, just a note on time. We have crossed the 1 hour mark and we have about half an hour left.
Okay. I'll try to finish. Yeah. So for the positive curvature case, one can determine which of the two saddle points dominate by comparing the value of this classical action at these two saddle points. Okay. And for L less than 2 pi, there's a critical value of mu below which this large disk dominates, and above the critical value of mu, the small disk dominates, as one would expect. If you increase the bulk cosmological constant, then smaller disks would be favored, because if the area is going to, a larger area is going to cost you more. So that's why the smaller disk would be favored. And so this critical value of where this transition happens, this can be found for each. So if we define x to be L by 2 pi, and I'm just calling y equal to mu. So this critical value is given by a curve which is like ycx. So corresponding to each value of x, there will be a there will be a yc, and then y is greater than yc, then the smaller disk would be favored, and when y is less than yc, the larger disk is favored. Okay, and the equation that is satisfied by this yc is this. You just compare the two classical actions, you evaluate, you have the saddle point value, you evaluate the classical action at the saddle point value, and just compare for the two saddles, and the one that dominates is determined by this value of y, whether y is greater than yc or not. Okay. And the leading order term f0 eta in the perturbative expansion of the log of the partition function, this can be obtained by evaluating SCL at the respective saddle point. So for eta equal to 0, we have f00, which is minus 1 over 6 ln L by 2 pi minus mu L square by 96 pi square, some numbers. But for eta equal to minus 1, we have a similar expression, but more complicated. For eta equal to 1, again, we have an expression, but epsilon, now we have an expression for both for the large disk and the small disk. And epsilon, this parameter epsilon is 1 for the large disk and minus 1 for the large disk, for the small disk. And this is what you have to compare it, essentially. So whether which one is, so this is just f0 eta, f0 plus is just the log of, is minus SCL. So to compare, you can just check, one can compare the value of f0 plus for epsilon equal to 1 and epsilon equal to minus 1 and see which one is dominant. This is what I just mentioned. So, okay, so these are the leading order values which are just obtained from the saddle point by saddle point analysis. And while evaluating the subleading corrections to the log of the partition function, one should bear in mind that the loop integrals that one would have, like for instance, you have a quadratic action in terms of the boundary field xi. So that loop integrals, there would be some loop integrals when you try to compute the Gaussian integral, and these loop integrals would naively diverge. However, these divergences can be tamed by working in some regularization scheme, right? So, like for instance, you also have this bulk, the log of the determinant coming from the integral over the bulk fluctuation field. So those also need to be regularized, and one needs to work in some regularization scheme. And there's always an ambiguity associated with choosing such a regularization scheme. And this is just as what happens in any quantum field theory. I mean, like you have to choose some particular regularization scheme. And the difference between two such schemes can always be accounted for by appropriate counter terms. And they can be absorbed by renormalizing the different parameters. Okay, so this works here as well. And we have chosen to work with the zeta function regularization scheme to evaluate these quantities. Okay, so yeah. Okay, so at the subleading order, there are these terms, minus 13 by 12 pi SL evaluated at sigma star, plus sigma star by 2 pi by 3, plus sigma star by 4 pi by sigma star at 4 pi by 3. And these can be evaluated straightforwardly from the saddle point values of the field configuration. So once you have the saddle point configurations, you can evaluate this immediately. The term involving the bulk determinant, which is minus ln mod of determinant of d delta star minus 2 eta, is a bit more tricky to evaluate because you have to calculate this functional determinant with on a space with finite boundaries, and this was apparently not done earlier. So we wrote a paper in May where we evaluated precisely this quantity for the different cases for eta equal to plus minus 1, especially for the curve case. It's a bit more challenging. So we evaluated these this log of this determinant, and it turns out that this log of the functional determinant, this can be expressed simply in terms of some elementary functions and the Euler gamma function. Okay. I'm not giving the explicit expression because it's a bit long. So, but if you are interested, you can have a look at this paper that we wrote, this whose archive number is given here.
Can I ask one question?
Yeah.
So normally when one has to calculate determinants of this kind, one has to put a boundary condition, right? Because you want to look at the eigenfunctions.
Yes.
Some boundary
We impose
condition.
the Dirichlet boundary condition. Here it's the Dirichlet boundary condition. That's what this D subscript D indicates. We impose Dirichlet boundary conditions on at the boundary, and then we employ zeta function regularization to compute this determinant. So because naively there would be you have to perform a sum over the eigenvalues, and that would diverge. So that's where we have to employ the zeta function regularization to calculate this log of determinant.
So this Dirichlet boundary condition came from your original formulation?
Yes, because
imposed explicitly.
No, it came from the formulation because of the way we split this thing. Because we were the way we split this thing. Let me just go back there. So this came from the fact that we split the integral. So probably here. Yeah. Okay. So the point is that we denote this bulk fluctuation field corresponding to xi with the subscript small xi, right? And then we are imposing this delta function. So we have split the bulk fluctuation field into two parts. One is xi with the subscript xi, and then another part. The point is that the overall bulk fluctuation field, that its boundary value should approach to xi, small xi, and the part that we have identified as xi with the subscript small xi is a solution to the Liouville equation, but with the same boundary condition. Okay, and we are integrating over the residual field. So if we express the bulk fluctuation field as the solution to the Liouville equation with corresponding to a particular value of xi plus a fluctuating field, then this fluctuating field's boundary condition is 0, because the boundary value of xi of this capital Xi with the subscript small xi is also xi, and the boundary value of the fields of the whole field is small xi.
I see.
So the fluctuating field, in this way of splitting, the fluctuating field boundary value is set to 0.
Okay.
So that's how this Dirichlet condition on the fluctuating field appears.
I see. Okay, thank you.
Yeah. Okay, so where is it? Yeah. Right. So there is also this term involving the boundary path integral, log z boundary. And to
Sorry,
illustrate this,
Soumyadeep,
Yeah.
can I just ask some question about this log of the determinant B? This
Yes,
depends only on L, doesn't depend on mu. Is that right?
yes. It only depends on L. Yeah.
Okay.
Okay. So this log of the this z boundary, that the boundary path integral, this thing, to illustrate the significance of this term, we need to discuss the quadratic effective action, this S effective of the boundary field xi, that appears in the boundary path integral. And let me tell you the explicit form of this boundary action. So to write this boundary action, we can, let me just remind that this field xi must be periodic in the angular variable theta, right? Because we are considering a boundary field defined over a circle. So it should be periodic under theta going to theta plus 2 pi. And then one can do a Fourier decomposition of this. And the xi-n's should satisfy the condition that xi n star is equal to xi minus n, because the field xi has to be real. So after doing this mode decomposition, in the flat case, this quadratic action of the boundary that appears in the boundary path integral takes this form. So notice that the sum runs only over n greater than or equal to 2. So there's no n equal to 1 term. Okay. So the field xi1 or the xi minus 1, they don't enter into the effective action. And the same is true for in the curve case as well. Okay. But this is important. The point is that the integrals that we the constraints that we imposed on this boundary path integral, which arise from the PSL2R gauge fixing as well as the constraint of overall length, these delta functions impose the condition xi0 is equal to 0, and hence this term involving mod xi0 square, this vanishes once you impose the delta functions. And moreover, they fix this value of xi1 and xi minus 1. There were 3 delta functions, right? 3 delta functions corresponding to the 2 PSL2R gauge fixing conditions and the overall length. So one of them kills the mod xi0 square, and the other 2 fix the modes xi1 and xi minus 1 in terms of the other modes. So hence, despite the action being independent of this xi plus minus 1, the integral over these modes do not lead to any divergence. And hence, so because of these delta functions, one can just perform the integrals over xi0, xi1, and xi minus 1 trivially. And one is left with the other modes, that is the modes for which mod n is greater than or equal to 2. So the integral over these remaining modes are convergent only if the coefficients of mod xi n square in the quadratic effective action are positive for all n greater than or equal to 2. Otherwise, if they are not positive, if they are 0 or negative, then there would be some tachyonic instabilities in the respective saddle, right? So by demanding the positivity of these coefficients, we get a domain of stability of the respective saddle. But one thing to remember is that this is only a local stability. I'm talking about a local stability of the saddle. This does not ensure that globally that saddle point is actually the least, the point where the potential is minimal. This whole analysis is done around the saddle, and this, by stability of the saddle, I mean just the local stability of the saddle point. Okay. So for eta equal to 0, this domain of stability is given by mu L square less than 24 pi square. So the cosmological constant has to be sufficiently small, basically. For eta equal to 1, similarly, the cosmological constant has to be sufficiently small, and the upper bound on the cosmological constant for which there's no such tachyonic instability, this is given by this expression. So y is equal to mu again, and x is equal to L by 2 pi. For the positive curvature case, as I had mentioned, there are two saddles, and each of them has a different domain of stability. So for the small disk, the cosmological constant has to be sufficiently small, where y is mu and x is L by 2 pi again. So y has to be less than some ys x, which is given by this expression. And for the last disk, y has to be greater than ylx, where ylx is given by this expression. So this picture that I've drawn here, I'm not sure how much of it is visible. So basically, the point is that there's this dark region here is this black line that passes through the middle. This is the critical line that I had drawn earlier, which shows the line across which the dominant saddle changes. Okay, and there's this shaded region, this dark region here is the region where both the saddles are stable, locally stable. And when you go out of this dark region, that is, if you are in these regions with lighter shades, there the dominant saddle becomes unstable, and hence the perturbative analysis is no longer reliable. That's the point. That only in this region, that is which is shaded, which has the darkest shade, is the perturbative analysis reliable. Okay. So that's the conclusion. And in the domain where the perturbative analysis is valid, one can calculate these values. One can evaluate the boundary path integral, sum over them using zeta function regularization. And that's what gives you, and if you add up everything that I had mentioned earlier, you get an expression of this form. Okay, so you have this f for eta equal to 0, the first subleading correction to the log of the partition function, the log of the partition function that takes this form. And similarly for eta equal to -1 and for eta equal to +1, you have similar expressions which are given here. Okay. So let me just come back to this issue that I had mentioned at the beginning of the talk. So from this perturbative expansion of the log of the partition function, we can now check this fractal nature of the boundary curve that I had mentioned earlier. So if we just, for simplicity, we can look at the partition function, the log of the partition function in the flat case, and you have this mod c times this thing. This is the leading order value, and then you have the subleading terms. So the thing to notice is that so there is this term minus mu L square by 8 pi square ln L by 2 pi in the subleading term, and that can be absorbed in the leading by modifying the leading order term. This instead of L by 2 pi whole square, here there is a term like minus mu L square by 96 pi square. You can change the power of L, or L by 2 pi rather, instead of raised to the power 2, if you take it to be 2 nu, where nu is given by this expansion 1 minus mod 1 by 6 mod c plus order 1 by mod c square, then you exactly cancel this contribution. So this shows that in order to get dimensionless quantities, like if L indeed has an anomalous dimension, then it has to be raised to something raised to the power 2 nu to get something that has the dimension of length square, which would then cancel the dimension of mu. Okay, so that's the idea. So that this is the way to show that or see that L indeed has an anomalous dimension in this model. And this expansion of nu that I've written down here, that comes from this from just this argument, that matches with the general expression that I had written down earlier for nu. And the same expansion of nu can be derived also from one loop partition functions of the curved JT gravity models. Okay, and this nu should not, because the fractal nature of the fractal nature of these curves, they depend on the microscopic UV properties of the theory. So this is independent. This does not rely on the curvature, essentially, whether it is zero curvature or positive curvature or negative curvature. This is just a property of the fact that of the UV nature of the theory, which is not set by the curvature length scale. Okay, so maybe I'll just finish with a short brief discussion of the Schwarzschild limit. So
Actually, Soumyadeep, can I ask some question about this
Yeah.
previous? I'm trying to
Yes.
understand the statement. Like,
Yes.
is this anomalous dimension of L, or is this like running of the cosmological constant?
Why do you
I
think
guess-
that it's a?
I mean, the way I would think about it is that you have a given L and a given length, right?
Yes.
And in some sense, you're kind of measuring the partition function at a given L, and you're trying to look at what is the cosmological constant, okay, at that L, so to speak, for a universe so big. Okay.
Mhm.
So, and then you see that there is some running. That's why I would say, I mean, in the sense that usually renormalization, we kind of say that, so you have some measurable quantity, some physical quantity, and then you ask, some effective coupling, how does it look like? How does it depend on that, right? So, this is what I'm trying to understand. So is this like fractal nature of the boundary, or is it like the boundary has a length
Because
L?
sorry.
But boundary. So I would say the boundary has length L, but the cosmological constant.
The point is that
Yes.
the continuum, as I was mentioning, the continuum limit, if you try to take if you start from a lattice version of the theory, okay, and then if you try to take the continuum limit if you take the lattice spacing to 0 while keeping the boundary length, where the boundary length is given by the number of, let's say, the number of lines that you have to draw in order to form the boundary, that you take to infinity. So when is this the point is that to define a sensible continuum limit, one may have to raise the power of this number of lines that you need to draw the boundary to an appropriate power, and then multiply by the lattice spacing and then take it to some constant. Okay, and this is how this nu appears in the continuum version of the theory.
But let's say if you're doing, let's say, lattice gauge theory, no gravity, no dynamical metric, anything, right? Exactly what you said would happen, and that's how you get like running, like anomalous dimensions from the lattice field, right? Like you have to scale, you have to scale some macroscopic length over the lattice length and with the power, and you have to take the continuum limit in the appropriate way.
Yes.
Let's say if you're calculating some lattice correlation function, mass of the pion, something like that, mass of the some. Yeah. So that's what you do. So we would not.
So then.
So in that case, let me finish. In that case, we would not say that the space-time becomes fractal. Space-time is not dynamical. Space-time is just is there, and over that there is a gauge theory. Okay.
Yeah, but the point is that in this case, what you call L is in that case the field itself is not a metric, right? In this case, since we are working with quantum gravity, the field itself is the boundary length is given by the field that is defined, right?
Yeah.
So hence this length is so the distinction in the two cases is that in this case the length is given by the field that is defined on this space, right? The sigma field, let's say, or the metric.
Maybe let me rephrase the question. In some sense, if you take a fractal and you ask for a length,
Yeah.
okay, in some sense the length is just infinite, right?
Yes. Yes.
So what is this L then? What is the
L is the quantity that so when you take the continuum limit, in this case, as I said, there's there is this the lattice spacing times something times the microscopic length raised to the power something that should go to a constant, right? L is that constant essentially in this case.
Yeah, but that is not like very, see, that is, you want to define things without making contact with the lattice, right? You want to define things which are in the continuum limit, like what measurement will you do to measure L? Because you can't measure the length of the boundary. As you're saying, it is a fractal. If you try to measure it, you will just get like not an L, right? This is what I'm saying. So this is why I think it's better to think of it as, okay, so L you measure and L you fix the boundary, length to be something. And then you can imagine that you're measuring some cosmological constant, okay, which is running, which you would expect to run, right, in general. So anyway, but I guess it's a question of interpretation, but I'm just trying to understand why this interpretation is why this is anomalous dimension of length parameter as an anomalous dimension of the cosmological constant.
In fact, I mean, if you work away from this semi-classical regime, then I'm not even sure there's a length parameter at all, because it's some fractal that whose length, what is the length for that? It's only because we are working in this C tending to minus infinity that you do have a notion of length, where this makes sense. This otherwise this e to the power this e to the power sigma thing is a random distribution, right? So it's not in the finite C case, it's not even clear to me what you mean by length.
Okay.
So
Okay.
that's why I don't think that the correct way to think about this is that there's a finite length and then you allow the bulk cosmological constant to run, but rather there's a genuine fractal nature of the boundary. It's not like that you can take this, and the way to understand this is, at least the way I understand this, is in terms of this lattice model, where you have a renormalized length parameter which is given by this, the lattice spacing times the microscopic length raised to the power n, that raised to the power raised to some power 1 by nu, let's say, and that is equal to something that goes to something. That's how the continuum limit is defined, and L or beta, what I was calling beta earlier, is that parameter, and that's what defines the continuum, the theory in the continuum limit. Okay. Because so that's yeah. Okay, so yeah. So let me just finish. So the Schwarzschild limit is so the point is that most of these works on JT gravity have studied the theory in the Schwarzschild limit, and it is a limit in the negative curvature model where an effective long distance description of the theory emerges from the microscopic theory. So we would like to reproduce this result, this Schwarzschild limit, the results that are known for the partition function in the Schwarzschild limit. And to do that, we restore the length parameter capital L, which we had set equal to 1. So to define the Schwarzschild limit, we consider this L by small l by the length, the boundary length by capital L going to infinity, and mu L square going to minus infinity. And in this regime, one can check from the expressions that I had given earlier that the partition function, or expression for the partition function, that the expectation value of the area, which is just given by this partial derivative of log z with respect to mu, this is capital L times some effective length parameter in this regime. Okay. And this effective length parameter is of this form. Up to the approximation that we are working, that is up to order 1 over mod c corrections, it takes this form. And one thing to note here is that this nu times 1 plus xi, this xi is different from the boundary field xi. This is just an exponent, critical exponent. So nu into 1 plus xi, this is equal to 1 up to order 1 over mod c. So this ls scales linearly with L in this regime. Okay. And we conjecture that this is also valid at higher orders in this 1 over mod c expansion. So the renormalized length parameter, the Schwartzian length ls is going to scale linearly with the renormalized length parameter. Okay. So then once this ls, this length parameter ls is defined, the Schwartzian limit is defined as ls by L going to infinity and mu L square going to minus infinity. While this ls by mu mod mu L cube, this thing is kept constant. Okay. This is equal to, this constant is, I'm calling Bs. And in this limit, the logarithm of the partition function, this can be expressed in this form. Okay. So you have this log Bs term, and then there is this term like, which is the saddle point value mod c by 4Bs. And finally, we can define beta s to be Bs by 2 to the power xi mod c, and we get this expression for z minus up to this approximation that we are working in. So beta s to the power minus 5 by 2 e to the power 4 beta pi by 4 beta s. And this is the expected behavior of the partition function in the Schwartzian limit, modulo an extra factor of 1 over beta s. And this additional factor of beta s in the usual treatment, that is, you usually have beta s to the power minus 3 by 2 e to the power 4 pi by 4 beta s. This additional factor of beta s appears in the usual treatment because of a mark point on the boundary. So, for instance, this is discussed in Stanford Young's paper as well. So you have a mark point on the boundary, and this beta s appears in the this additional, it's beta s to the power minus 3 by 2 when you have this such a mark point. But in the treatment that I gave, there's no such mark point. So that's why you have this relative 1 over beta s factor in our case. So as I mentioned earlier, this Schwartzian description is an effective IR description of this model that emerges at energy scales much lower than the UV cutoff set by L in the dual holographic theory in the SYK-like model. Okay, so let me just conclude. So in this talk, I presented a perturbative analysis of JT gravity on a disk coupled to conformal matter in a semi-classical regime. And this analysis is quite similar to that of Liouville gravity coupled to conformal matter. And in fact, for this Liouville gravity on a disk, we have been able to reproduce the results of FZZT in the large negative C regime which we were considering using exactly the same techniques. Okay, so the only thing is that this bulk part, the integral over the bulk fields would be different, because you would have, instead of this Jacobian, you will have you have to integrate over the bulk modes. Actually, there's no constraint of constant curvature in the Liouville gravity theory, so you have to integrate over all possible bulk modes. But it can be done. It can also be done in this regime, and it reproduces the results that were obtained by FZZT. FZZT obtained an exact result. Here we are able to reproduce those results for Liouville gravity in the large negative C regime. Okay, so it would be interesting to go beyond this semi-classical analysis and find an exact expression. Like in Liouville gravity, you do have such an exact expression, which was derived by Diozisi for this for sphere for a manifold with the topology of a sphere, and then later by FZZT for the disk. So it would be interesting to find similar kind of exact expressions of partition functions or correlation functions in for general values of C instead of this C tending to minus infinity, including the case where C is equal to 0, that is just pure JT gravity. Okay, so such a finite cutoff path integral is has not been done, but it would be interesting to see. And what our analysis suggests is that many of the ideas that have been employed to study Liouville gravity can possibly be extended to study JT gravity as well. From much of what I mentioned is basically the same. The ideas are that you have in Liouville gravity, one may be able to extend them to resolve these questions in JT gravity. So finally, it would also be interesting to look at higher topologies. Here I was looking at the disk. So it would be interesting to look at higher topologies. And it would also be interesting to develop a similar microscopic understanding for the real-time version of JT gravity, which I don't think one has right now. Yeah. So yes. So with that, let me conclude my talk. Yeah.
Thank you, Soumyadeep, for the nice talk. Are there any questions, comments? Does anyone on the Zoom have any questions or comments to make? Okay, so if there are no further questions, then let's thank Soumyadeep again. Yeah, thank you.